over. Our next presenter is Dr. Cruz. He didn't give me a bio, so I made one up.
Uh-oh.
And here goes. I don't know if you all know this, but he was in a rock band in the late 60s and early 70s. And the name of the band was Asphalt Rocks. And the CD will be for sale outside if anybody wants one. But a couple of, he also wrote the songs in this thing. And if you do go to YouTube, you can find him on there. But one song that he wrote was, and they were kind of a rockabilly kind of a band. It was, She Thinks My Paver's Sexy. And the other song that he wrote, which was the real famous one, is War Mix, I Think I Love You. Very famous song. So I'll play them for you sometime if you want to hear them. So with that, I think you're going to not talk about music, but graphene, is that right?
We're going to talk about graphene. Yeah.
Okay, yeah, all right, thank you.
The sad fact of the matter is that that's all true. And much to my chagrin, it's still on YouTube. And my children found it. My daughter found it the other day and said, Mommy, my wife Maria, is that Daddy in a wig? It was. Anyway, I am going to talk, as Mike said, about graphene. As I mentioned yesterday when Buzz gave his presentation on plastics, we have a session here. The next 4 presentations are looking at innovative materials that are being investigated for application in bitumen as modifiers for bitumen to enhance certain properties, or in the mixtures to enhance certain properties. And earlier in the fall, I don't remember where I was, but we were seeing or hearing from our colleagues at Ingevity in Europe that companies were investigating use of graphene of some type in pavements there, and what's that all about? And so we started looking at it, and I ran into John D'Angelo somewhere, and he said, oh yeah, we looked at that. In fact, he told me that Galen and he had been invited to Washington to talk or to hear some stories about the potential for graphene use in bitumen, in pavements. So when John told me that, I said, I think he even offered, I have a slide presentation on this. I said, can I have it? He said, sure. So this is mostly John's slide presentation here. So thanks to John and to Galen. This is graphite. It's a mineral, close to 100% carbon. It's made through metamorphic processes, lots of high temperature crushing of sedimentary, high organic sedimentary stuff, gets crushed under geologic time frames and lots of heat, and it turns into this carbonaceous stuff. And of course that's graphite too at the end of that pencil. So we're all familiar with graphite. What graphene is, though, is something completely different. It is, it's in the graphite, in that ore, but the graphene refers to, and I don't remember where the name came from, but the graphene, it fits a little bit of organic chemistry nomenclature to call it graphene. The graphene are these single layer, 1 carbon atom thick layer, as it shows here. They're 3.4 angstroms, 0.34 nanometers thick, and essentially infinite in the planar direction. And these materials have very, very interesting properties. It is a form of carbon, and these are the other forms of carbon that we're familiar with. The pencil lead, or I call it pencil lead, the pencil graphite, the carbon nanotubes, the buckyball, the fullerene structure. These are called, they were phenom in the 80s. These forms of these geodesic dome forms of carbon, and they were named after a guy named Buckminster Fuller, who got the first patent on the geodesic dome. He didn't actually, like many patent things, there was somebody else that had actually invented it, but he got the patent. or had disclosed it somewhere. But Buckminster Fuller got the patent on it. And of course, some people's favorite form of carbon, tomorrow, Valentine's Day, if any of you guys have forgotten, that's a favorite form, the diamond. And so anyway, so graphene is kind of, oh, these are all called allotropes. Just different forms of an element, not molecules, but different forms of an element, chemical forms of an element. It's interesting the way in which graphene was isolated. It was isolated. It's got a very fancy name if you look in the patent literature. It's got a very fancy name for taking a piece of Scotch tape and pulling off layers and layers and layers and depositing them over and over and over again on silicon wafer so they could be studied. And these two guys, André Guim and Nostosya Nokolov, something like that, on the left and right, got the Nobel Prize for that in 2010. And so a little Scotch tape, a little graphite, and quite a big prize. I don't know what the Nobel Prize award was, but it's usually in the several hundred thousands or a few hundred thousands. Anyway, that was the guy. Those were the guys that did that. Why a Nobel Prize for pulling graphene off of a piece of graphite? Well, it's because these materials have just these absolutely, graphene again, I want to emphasize that point, graphene, those sheets, those monocarbon layer sheets, kind of infinite in one direction. I should have mentioned this for the chemists in the room, they are polynuclear aromatic. If that means anything, but that's what they really are. And that, in turn, that feature, that it's an aromatic feature in these planes, gives them a lot of these properties as regards conductivity and electrical conductivity and thermal conductivity. But these highlight some of the features that have been discovered about this stuff. It's really tough. It's got extremely high tensile strength. It's got really high tear strength. I can look this way. It's got it's the world's best electrical conductor. And I got on the next slide, I show you some of the rankings compared to copper, for example. And that's because, again, for the chemists in the room, that pi cloud on the bottom and top of this thing allow electrons just to move almost, if you read the literature, it's really kind of neat. It's very neat the way these electrons are behaving according to some equations that were developed back in the 20s, early 30s, trying to link quantum mechanics to Einstein's initial theories on relativity, because there was a disconnect back then from quantum theory to relativity theory, and there was a guy that came up with some equations that linked those two. These materials behave a little bit like metals, but a little bit like the metalloids, the things that are, well, the silicons and geraniums and that sort of thing. So it's a very interesting material, and people are fascinated by it. Best conductor of heat, it's flexible, and it's very stable. What's not on here is the fact that, well, here's a list of some things I added to John's presentation. Strength, compared to steel, which has a tensile strength of, according to the literature I found, 505 megapascals. These graphene sheets, I won't spoil the presentation here. These graphene sheets have been calculated or measured to have 130 gigapascals. And I don't even know what that is in PSI, but it's a huge, huge number. They have impact resistance. You'll see a slide on that. So people are looking at them. There's a company that's investigating use as a thin anti-bullet material. Thinness, very low density, and I calculated that 5 grams would cover a soccer field, one sheet. So just really neat. Thermal conductivity, order of magnitude bigger than copper. Bipolar, that has to do with that. The bipolar is, again, if there's an electrochemist in here, forgive me, but bipolar means it can move electrons or it can move valence, holes, kind of like we need in electrical microcircuitry. It can move electrons or it can move a hole, if you will, or a valence, so it can do both. And it's almost completely transparent. 2% absorption of light is I didn't know this before, 2% absorption of light, incident light, is heretofore unheard of. Oh, the other thing that I thought was interesting too, it's a barrier to almost everything but water. Water will go through it, but no gases will go through it. And if, again, if you think about these aromatic rings, I never thought about this in school or anything, but they do theoretically have a hole in the middle of that pie donut. And so maybe somehow a water molecule, which I think is bigger than that hole would be, can get through, but nothing else can get through. So there are people speculating it's a way to clean up water, for example, from radioactive nucleotides, because you'd hold the nucleotide on one side and the water would come out the other. Really, just amazing, amazing stuff. So, you read in the literature, people are calling it all sorts of fantastic prophetic things like material of the millennium. People say, oh, we started a civilization in the Bronze Age, and then went to steel, and then went to last century the plastics, and then the Silicon Age, and we're talking about graphene becoming the age of graphene. And I put this in here because I thought it was kind of neat too. Given that tensile strength, if you looked at the cable diameter on the San Francisco Bridge, each cable has a cross-sectional diameter of 6,705 square centimeters. The equivalent tensile strength from these fibers would be 0.52 square centimeters. Yeah, it's just mind-boggling. It's mind-boggling. But these are what scientists and people are reporting. This is that ballistic study. This is from a study, Michigan, I think, is where they did it. And they fire these micro bullets, if you will, at this fabric at speeds equivalent to or exceeding the fastest bullet that we can fire today, and they don't go through. So it's, again, interesting property. And for that, people are trying to start to capitalize on whether or not it can be used. Golf balls, tires. If you want to learn more about it, there are websites, Graphene Info. There are a lot of websites on this, and I screenshot that title page for Graphene Info, and you can't see the index topics that are on there, but it's pretty amazing. And in there is where I got a lot of this information about what the properties are. There's a journal, and I think John got a lot of his information from Nixine Journal, all about graphene. This is the challenge we have right now, though. We can't really make it in bulk. So all of the studies that are being done, I think, are being done on these really, really tiny, isolated, difficult to isolate samples of these monoplatelets. The two main ways that it's being done right now are the chemical vapor deposition and this electrochemical exfoliation. Those are the two main ways it's being done, which I won't even try to talk about it. A lot of people working on it, though. This is a list of patents that have been awarded. I forget what the date was, but it's probably last year. Patents, a lot of research in Korean institutes, probably in consortium with, or in conjunction with Samsung there. You can see they have 16 patents, both for the materials, apparently for materials transparency, as well as for these bizarre electrical conductivity properties it has. Again, this is a repeat sort of CVD and exfoliation are the main ways it's being done right now. The challenge is, and I threw this slide in, the challenge is you've got to make, for these things to do all of those super material properties, you can't have defects in the material. And so this is a slide that shows these blue, magenta, and chartreuse things are representing defects in the material. And you can't have those if you want them to have super properties. And so that's where a lot of the work is right now, how to make them without these defects. The literature likes to point out that that's where we were with silicon wafers a generation ago, and we conquered that problem. And so we all have our collection of all world history in our back pockets today in our cell phones because of the ability for us to have figured out a way to get those silicon wafers to work properly without defects and to produce them in bulk. We're not there yet, and for that reason, these little wafers, I just went online to figure out what one was, can be anywhere from, this is a tiny, tiny little sample on a piece of silicon or a piece of copper, I forget how they sell them, up to $900 per wafer. John's got some other information in there about pricing too. But the point being is that, like the golf ball, like the tires, it's new, strength, tensile strength, all the things we want in our pavements, resistance, do they help in pavements? And I know a couple of people in here, Aaron and Jeremy, have familiarity with it, but if you haven't been keeping up with the literature in this area, we are looking at, in pavements, we are looking at graphene derivatives, I'll say, in bitumen. And Interchemica is a company doing it. Directa Plus, I think, or Directa Plus is working in conjunction with Interchemica, an Italian chemical company. And a project was done. There have been a couple of projects in Europe, as I mentioned at the opening of the presentation here. It was my colleagues asking about this stuff. Skanska is a contractor up in the Scandinavian area, and they did a project. Most of the trade articles that you see from, like this one, Construction Inquirer, those kinds of magazines, they talk about what was done, and of course they, like often we see in our trade magazines, they're not peer-reviewed scientific reports. So they talk about all the great things they saw in the material, but we still need to go back to the peer-reviewed literature to find out if anything works and how it works, what the shortcomings may be. And so there are peer-reviewed papers out there, and I've included a couple of them here. I'm not going to go through all of them. I'm going to give you the conclusions right now in these papers. And actually, I want to jump ahead because I wanted to make a point here, is that to the best of my knowledge, in these studies that have been done with a view toward determining whether or not these materials work in bitumen and what they might do, they're not really looking at graphene, which is the super material I talked about in the first 53 slides. They're looking at things like, they're looking at graphene derivatives, like graphene nanoplatelets. So a graphene nanoplatelet, again, based on my understanding of the literature, are assemblies of these graphene. They're not these individual sheets. And you can look at these data at your leisure when these presentations come out. You can see down here the tensile strength of actual graphene was 130 GPa. It's 5 here. So they're different materials. The specific surface area, that specific surface area won't cover a football field with 5 grams like the sheets do. So they're different materials. So that's what's really being studied. And this is from a master's thesis at Norwegian University, and they doped with these. And that's the thing, be careful if you're interested in this. When you get into the literature, they'll say graphene, but you got to look closely because it's GMP, it's graphene nanoparticles. And you'll see here they're doped. Whoop, I don't have to go back. Okay, go back. Here we go. They're doped at a couple of different levels. They're meeting PG grade, but they are kind of pushing the low failure temperature in the wrong direction with the more material you put in there. In this particular study, and I don't remember what the binder was, where it came from. It was probably a Scandinavian binder. This I thought was important for us to note. These are the recovery values down here for these samples. If you remember, this is your what we call sometimes the polymer line in the massacre test. So anything up here is behaving like a polymer modified material with resilience. It's got a high percent recovery for that JNR value. Yep, for the JNR at 3.2 kPa stress. You can see down here, these are stiff-ish, but they don't have any kind of the percent. They don't have percent recovery in this study. Mihai Marestino has studied some different GMP graphene nanoparticles. These are the materials he's looked at. He's published in several different locations. He published back in 2016 at the Euro Asphalt conference in Istanbul, and he's also published his results elsewhere. So again, you can go look at your leisure at these documents to get more information about what they did, what their experimental design was. Here's another NCHRP idea proposal to study these materials. And in that, he took these, again, GMP particles, characterized them, ran BBR on the materials at a bunch of very low temperatures, and did flexural strength studies, and these were pretty much the conclusions. The ones in bold, on the 3 bullet statements on top in bold, are my summary, and then this paragraph was excerpted from Mihai's paper, and he told us that we could take his data, by the way. I don't have it, but he said it would be okay to put it in here just to show you where things are going. Again, pioneering work, maybe or maybe not. We find where it fits, it still needs to be done because of these super properties the material has in its very pure form, not yet readily available form. Here's another study. The results stiffened. Optimum binder was increased. We know that happens sometimes. Buzz talked about that yesterday. You modify something, and if you do your volumetric mix design, you may or may not see that you need a higher OBC. Ductility decreased, which is probably something many of us would view as the wrong direction to go with ductility. And then the wheel tracking improved. They only went to 10,000 cycles and improved 3 millimeters. I don't know. I don't put a lot of. Depending on how you run your Hamburgs and things like that, I mean, 3 millimeters is a couple of credit cards thick, so it may or may not be a significant observation. If it was run on 11 LVDTs on a Hamburg or something, maybe it is. But anyway, it moved at 4% GMP. Some tribology work was done. Again, it's being pursued. One of the challenges, though, the pure stuff, if you calculate what it's being sold for right now, it's a wee expensive, at $90,000 a ton. And John calculated that at 0.5%, by weight of the binder, it would add probably a little bit too much to the cost of a ton of material. But again, I just thought it was very interesting. It's getting attention in different parts of the world, and I wanted us, being the Association of Bitumen Modifiers, to be aware of what's being investigated. Yeah, field trial in Italy. It was one in the Netherlands, and then I showed you the one in Scandinavia somewhere with Skanska. As I mentioned at the beginning, John and Galen were invited up to Washington to have a conversation about this stuff. And so people are interested. Anything that can make our infrastructure better, we have to pay attention to it and investigate it. And according to John, there's a ALF section at LSU, right, that may be including this in something in the future, in a Mississippi field trial. Thank you.
Any questions about graphene? Oh, there's one. There's two.
Would the conductivity be a cause for concern, or how would that affect if it was
Thermal
put down?
conductivity or electrical conductivity? The thermal conductivity I've seen in the literature highlighted as a benefit. I don't get that, though, because why would I want to bring more heat into my pavement? Deformation, maybe accelerated oxidation at higher temperatures, those kinds of things. And then we go to warm mix to reduce those kinds of things from happening. So the electrical conductivity, though, I've seen discussed as a little, it's not happening tomorrow. So it's one of these, we could do this in the future. They talk about, the road being instrumented effectively with micro graphene somehow. So the electrical conductivity may be in that regard. Thermal conductivity, it seems a little bit contrary to what you might want.
Thank you. Somebody else back in the back? Question went away? Excuse me, I'm slow.
This is Musi. I was going to ask you about the price, and if you go back one slide to the slide that shows the pricing. Yeah. So this one, can you comment on the feature pathways to reduce this? Because there is no question on the functionality of the Pavement, this graphene. It has so much functionality on it, but the pricing seems the limiting factor because, as we know, asphalt is much cheaper product. So if you bring in this very expensive material into a very cheap product, that is where the problem right now. And then, do we have any roadmap to actually consider this?
Yeah, good question, Musi. To one of the slides I showed, I think it was the work by Mihai. I think they had the pricing in for the GMP, the graphene nanoparticles, not graphene. That's why I was trying to distinguish one from the other. I mean, think graphite, graphene nano. This is the way I view it. You got graphite, your pencil. You got graphene nanoparticles. So cost would be here. Graphene nanoparticles, graphene on the rooftop terrace somewhere in terms of the pricing chart. So you're absolutely right. Right now, the graphene in the binder, graphene, these monolayer sheets of polynuclear aromatic carbon, high, with all these super properties, yeah, that's not going to work. But that takes us back to that hope, and I know hope's not a method, but it takes us to that hope that we will be able to manufacture this stuff in bulk, and by manufacturing in bulk, it'll push those prices back down. If you can get, I don't know if you can get from 90,000 a ton or not. But I will say this. I remember many years ago looking at a magazine, and I forget the name of the magazine, but it was a magazine for high-end products. Magazine that, of course, I could have never bought anything from. But in that magazine was the first flat-screen TV I'd ever seen. Tiny little flat-screen TV. I don't remember what it was, but it was small. It was $25,000. Hemrick or Schumer or something like that. Anybody know? There used to be a magazine or something, I can't remember the name of it, but they would sell all these high-end products in there. But that flat-screen TV, this big, was $25,000. We bought, my wife and I forget what Maria bought it for, but she's got this massive thing in our bedroom now that was, it's like 66 inches or something like that. I think she paid $600 for it. So that economies of scale, if you can ever figure out how to do it, it goes down. This has wafers in it. I don't know what the wafers were or the circuitry actually cost when we first started developing it, but I remember my first handheld Hewlett-Packard calculator that could do probably basic mathematics was like 60 bucks, or I mean, no, more than that. I think it was like 200 bucks for the first little thing that had 5 basic functions on it. Now, well, we don't even buy those anymore. We just use our phones. But at any rate, download a really high-end math app. So you're right, Musi. I think that right now this is not going to fit the economics of our industry. But the idea of presenting all this information, as I mentioned yesterday, or my idea for wanting to do this, is that here's something really exciting in some industrial sectors, in some application areas. It's being investigated in ours. Will it get legs? We don't know. Will there be something that turns it into those Buckminster Fullerene things? Because they were very exciting. What will they do if we put them here or there? And they never, those dreams were never realized. But this has, as I showed from the patent activity, the amount of work that's, the amount of funding that's going into this. I didn't show those slides, but there's a lot of money being invested into it. Whether it ever makes its way, for the reasons that you said, into pavements, we don't know at this point. But I wanted our membership to be aware of what's going on.
Very good, Everett. I mean, Doc.